Climate-induced sea level rise and extreme wave action have created an unforgiving math problem for coastal communities. Every year, ocean kinetics grow more intense, outmatching the defensive structures we built decades ago. For over a century, the default engineering response has been the static seawall, single-purpose barriers of rigid concrete and tetrapods built solely to stand in the way of the water. But rigidity creates a physical vulnerability. Rather than dissipating wave energy, solid walls reflect it outward. This creates a scouring effect that strips sediment from the seabed and gradually undermines the exact foundation the wall sits on. To understand this failure, engineers track Metocean forces, the combined meteorological and oceanographic parameters like wind velocity, tidal patterns, and wave height. The volatility of these forces is accelerating faster than we can pour new concrete. Billions of dollars are currently spent maintaining static defenses that actively erode the shoreline and degrade marine habitats. It is a massive capital drain that fails to address the underlying hydrodynamics of the ocean. Resolving this requires transitioning to a cyber-physical system. The software side of this system relies on a digital twin ocean, a high-resolution predictive modeling environment that simulates exact marine conditions before any material is moved. The hardware side replaces the static barrier with seawall-based marine ecosystems. These are multi-layered physical installations engineered to extract kinetic energy and support marine life. The two components operate in a continuous feedback loop. Virtual what-if simulations test variables and calculate outcomes, and those verified digital results dictate the physical construction. By matching predictive data with adaptive infrastructure, vulnerable coastlines stop being defensive liabilities. They convert incoming wave forces into renewable energy and restore local biodiversity. Building an accurate digital model requires global-scale observation. Programs like the Copernicus Marine Service and EMODNet map the oceans continuously using massive satellite arrays and in-situ sensors. This 3D schematic shows how disparate metrics, like water temperature, surface velocity, and bathymetry, are beamed into a central processing node. That node synthesizes the incoming telemetry to render a continuous, three-dimensional numerical model of the ocean, mapping variables from the surface down to the seabed. Every pixel in this model represents a mathematically exact, real-time data point, replicating the physical ocean environment with extreme precision. From this global model, coastal engineers isolate a specific location and extract localized Metocean parameters. They analyze the exact tidal currents, suspended sediment concentrations, and seasonal storm tracks of that single coordinate. Without this perfect mathematical replica, coastal defense relies on generalized estimates. Precise digital rendering is the absolute prerequisite for designing physical infrastructure that will actually survive. We can test the predictive power of this model in the Wadden Sea, a shallow tidal region in Germany facing persistent coastal erosion. Instead of building a wall, the proposed intervention is biological, reintroducing seagrass meadows to act as a natural friction layer against incoming waves. This interface shows the digital twin parameterization environment overlaying the coast. Engineers use control toggles to adjust variables, like seagrass density and exact placement. By manipulating the simulation, increasing the density parameter, and shifting the position lower on the seabed, we test the intervention under extreme weather. The system calculates the hydrodynamics and returns a visual heat map. The colored zones highlight a direct, quantified reduction in wave impact and coastal erosion. Software simulations prove the mathematical survival of an ecological intervention before a single seed is planted. This reduces the risk of physical engineering failure by verifying outcomes against extreme weather events. While biological friction works in shallow tidal flats, other coastlines require heavier infrastructure. We see this along the high-energy impact zones of the Kerala coast in India. Locations like Shangumugam Beach and Chelanam suffer from severe seasonal erosion. Existing hard infrastructure continually fails against the intense monsoon waves. At the Muttalapoji breakwater, unscientific construction has actually increased local hazards. The structures reflect wave energy unpredictably, creating dangerous navigational conditions rather than safely dissipating the kinetic force. Engineers now rely on comprehensive geospatial mapping and continuous geophysical data collection to isolate these exact erosion hotspots. The data reveals a clear engineering mandate. Modern coastal structures cannot act as blunt blockades. They must be designed to dynamically interact with the ocean's mechanics. To survive these environments, the physical layer must absorb and harness incoming kinetic energy. The objective shifts from rigid defense to mechanical integration. This diagram displays a cross-section of a 3-zone seawall-based marine ecosystem. The outermost section is Zone 1, the energy capture zone, embedding wave energy converters and wind turbines directly into the aquatic approach. As the turbines extract kinetic energy to generate power, they physically attenuate the wave's impact long before it reaches shore. What diminished force remains strikes Zone 2, the structural barrier, an engineered concrete core providing absolute flood protection for the community behind it. Finally, Zone 3 integrates nature-based solutions into the inland side of the architecture, merging the hard barrier with biological systems like dense mangrove forests. Mangroves and salt marshes act as biological shock absorbers. Their complex root systems physically lock sediment in place, preventing erosion while simultaneously capturing atmospheric carbon. Because these integrated structures restore marine habitats, they attract aquatic life. This ecological recovery directly translates to higher yields and better sustainability for local commercial fisheries. This multi-purpose integration fixes the mechanical failures of traditional static walls while actively reversing the ecological damage those older structures caused. This approach operationalizes the principles of the blue economy, a framework aligning the sustainable use of marine ecosystems with targeted economic development. By integrating hardware that generates renewable energy and restores commercial fisheries, the coastal defense system creates direct, measurable economic returns. This flowchart maps the integrated model. Raw data informs the digital twin, which engineers smart infrastructure, yielding renewable energy and economic return. That return creates a feedback loop. Capital routes into reinvestment, while new infrastructure provides continuous data back to the digital twin. By adhering to this cycle, seawall projects stop acting as public liabilities requiring constant sunk capital, and they become sustainable, self-funding financial assets. Modern coastal resilience requires a continuous pipeline, pulling raw satellite observations from the cloud and transforming them into multi-purpose physical infrastructure. High-resolution digital models have evolved from simple disaster predictors into proactive, highly accurate engineering blueprints for the built environment. By engineering cyber-physical ecosystems, we stop fighting the ocean. Complex Metocean data becomes precise insight, and that insight becomes sustainable action.